So thank you all for coming back. I'm glad I didn't manage to scare you away yesterday. Maybe I'll succeed today. We'll find out. So let me try to, so I almost finished what I wanted to say yesterday, but I do want to review what this was. So our very naive setup was as follows. We had tau, which was an element in the upper half space, which is just to say this was a complex number, such that the imaginary part was positive. And we had z, which was just a complex number. But we really wanted to view z as an element of the elliptic curve. The elliptic curve is a genus 1 Riemann surface, which was just, oops. I'm sure as I go on, I'll get more tired and I'll make more mistakes, so please correct me. So the genus 1 Riemann surface is just a quotient of this, so we have this mental picture that that's what it is, right? That's an elliptic curve, and I sort of want to view z as lying in here. And we had a theta function, theta of tau z, which was the sum over all integers n exponential pi I n tau n plus 2z. Okay? And this has certain automorphic properties, as we discussed, which for me meant that theta was a section of a line bundle here called capital theta, which is just a way to say that under the transformation of adding a point in here, an integral lattice point, to the argument z, theta transforms the way it does. Okay? That was my notation. And now let me carefully write the theta functions with characteristics. I'll run out of space, so let me maybe do a bad thing. I'll put this here. Okay. So yesterday I was talking about arbitrary characteristics. My main interest will be level 2, but anyway, so for any n, and for any epsilon and delta being integers from 0 to n minus 1, the theta function of level n, so level n with characteristics is an unfortunately quite a mouthful to say, epsilon delta, and you have to specify n even though it doesn't appear in the notation here. Tau and z was by definition some exponential factor, which is nice. Times the value of the theta function shifted by this. Tau's don't really look so good, but hopefully you'll forgive me. And so that this is an exercise, I can tell you what this really is. So this is the sum over all n and z of the exponential pi I n plus not try to write this formula by heart at any point, as I learned the hard way. But I will anyway. Okay. All I did is I basically added this to my function here. I may have made a mistake. And then there is a theta function of this of the higher order, which was that guy. Evaluated at n tau. Okay. This was our setup from last time. And what I stated at the end of last time, I'll keep this blackboard clear for the generalization in 5 minutes. So I'll move this up. There we go. And the theorem was that these guys, this higher order theta functions, for all epsilon in V mod n, are a basis of the space of sections of the nth power of the theta bundle. So this means there are 3 statements here. Statement number 1 is that if I add an integer lattice vector here to Z, the transformation will be the nth power of the transformation formula for the theta function. That's statement number 1. Statement number 2, that if I do this for all epsilons, they will be linearly independent as functions of Z. They don't satisfy a linear relation. And the third statement is that they form a basis, that any other automorphic function of such a kind in Z is the linear combination. Okay? And then there was a formula which will play a role, which is the n equal to 2 case, which says the following. I wrote yesterday just the formula for theta. There is a slightly generalized version which allows this shift. Okay. That's the formula. So yesterday I didn't write epsilon delta, so there was nothing here, there was nothing here. So in general, this gadget here, this is only for n equal to 2. This is a section of 2 theta. It transforms as a square of the theta function. So it must be, as a function of Z, a linear combination of these guys with some Z independent coefficients. These are the Z independent coefficients. You'll know in half an hour to compute how to determine them. Okay? That was the statement last time. And one thing, this is all basically last time, except I added a bit more stuff. And here there is a remark or an observation, or maybe a fact. So I can take my Z, this is for fixed tau, and I can send it to the value of, one theta function divided by the other theta function. Okay? This is for n equal to 2. From now on, n is always 2. So there are only 2 second-order theta functions. This is a well-defined map from an elliptic curve to P1. Because if I add to Z a lattice vector, this guy and this guy transform the same way, so the transformation cancels. This is why it's important to understand that there are sections of the same line bundle, so the transformation law is the same. So this gives me a degree 2 map. In fact, you can compute the degree because that's the degree of the line bundle, which is 2. That's a degree 2 map, so this is a 2-to-1 map from an elliptic curve to P1. You probably know what this map is. It's the usual double cover, okay? There is also a version for n equals 3, which I'm not going to write. For n equal to 3, there are 3 of these guys. So I get a map to P2. And that's an embedding in P2. And that embedding in P2 satisfies precisely the cubic equation that is your usual defining equation of the elliptic curve as a cubic, okay? Which I won't write down. Okay, so now is your chance to ask the questions before the G will appear on the blackboard. Is this all okay? So again, the theta function I view as a section of a line bundle on an elliptic curve, which is to say it transforms the way it does. The advantage is it's a holomorphic section of an algebraic line model in a compact algebraic variety. So there are finitely many of such objects, also finite tensor powers, which is to say this is things that transform as a power of theta function. So I get a host of relations as I try to explain in a philosophical way at the end of the day. Okay? Yes?
How we get the elliptic curve?
Yeah,
and you also said yesterday that you touched us, but nevertheless, formula for the vector.
Absolutely. You can write, what I'm not going to do, is you can write the Weierstrass function in terms of theta functions. The reason I'm not doing this is Weierstrass function is a meromorphic function. Okay? In the next lecture, which is whatever, not tomorrow, but the day after, we will talk more about how we think about sections of line bundles as meromorphic functions on Riemann surfaces, which I haven't done. This is somehow mentally confusing if you haven't seen it. The Weierstrass function is a function, but it has a double pole at 0. I don't know how to deal with meromorphic things so well in this language, right? So I can take the Weierstrass function. It has a double pole. I don't like it. So I need to multiply it by something that has a double 0. What would that be? Well, theta function has a 0 at one point. Okay, so translation of some translate of theta function, what is called theta 1, for me, theta with characteristics 1, 1, has a 0 at 0. So I'll take the Weierstrass function, I'll multiply by the square of that odd theta function. That will kill the pole, that will cancel the pole with a double 0. That thing now will be a section of 2 theta. Because I had a function, which was a meromorphic function, I multiplied by a section of 2 theta. So that's a holomorphic section of 2 theta. So what I said is I can write pair of z, this is the Weierstrass function, times theta 1, 1 of z point squared. That object, this is a function, it's not a section of a bundle, this is a section of a line model, has no poles anymore, so this is on my elliptic curve, a section of a square of the theta bundle. You can now figure out which section it is. It's a linear combination of this guy and this guy. You can figure out which ones. That's your formula for the Weierstrass pair function. Okay? It is much easier in this language for me to deal with holomorphic things only, which means I always clear denominators. Yes? The degree of, because the degree of, so the theta, the degree means I need to compute, say, the number of pre-images of 0. So I need to know in how many points this guy vanishes, right? But the theta function vanishes at one point with multiplicity 1. So its square vanishes at one point with multiplicity 2. So any section of the same bundle as that will have to vanish with the same multiplicity. Why is the multiplicity the same? Because you can compute the number of zeros by integrating over the contour. And all you're using for this is the automorphic property. So this means this thing has 2 zeros. I know where, but I won't tell you. On the elliptic curve, this also has 2 zeros. You might worry they will have the 0 at the same point. And then somehow the degree will drop. That cannot happen because an elliptic curve system does not admit a one-to-one map to P1. But in general, you have to worry about such things. Okay? More questions? Yes? N squared minus 1, what kind of results? No, so you would expect n squared such results. So the number of such theta functions is precisely n squared. Yeah. So we have n squared expressions in terms of an n-dimensional space. Yeah. So what you're, I think, saying is if I take, the general formula will have an n here. So this thing here, this was secretly an n, right? So the generalization will be for the nth power. So this nth power will be such linear combination. So if you look at this, at all these nth powers, there are n squared of them. They can be expressed in terms of a basis which has n elements. So this means the nth powers will satisfy n squared minus n linear relations, which you can write out. Interesting. They are quote unquote obvious. I just write this formula, and then it becomes a question of linear algebra. So there is no particular interest in them that I'm aware of. This is a basis, so this is a natural space. You can do this, but this is a matter of linear algebra at this point, right? Because I just try, you're just equating the coefficients. not intrinsically meaningful that I know of. Notice that the reason I fix n equal to 2 is, well, this is a classical story, but just the dimension of the space of things explodes very quickly, right? So there are more and more things. You can do higher n, you better have a good reason, because there is a whole host of n squared minus n and more relations, and you better be willing to deal with that for some good reason. But usually n equal 2 is best for most applications. Any more questions? I'm well aware that I have a question and answer session this afternoon. So if we are slow, one of the things I want to say will hopefully become a question from the audience. We'll address this in the afternoon. Okay, so now I want to talk about abelian varieties. Okay. You will hate me if you're taking notes because, okay, abelian varieties. So this is definition. A complex torus, a complex G-dimensional. I know people usually use D or N for dimensions, but that's life. A complex G-dimensional torus is usually called a torus. I'll write it G-dimensional. It's just a quotient CG by some lambda, where lambda inside CG is an abelian subgroup. So it's you can add points in lambda and get points in lambda, and I want lambda to be isomorphic to z to the 2g. So this generated by 2g vectors, 2g complex G-dimensional vectors, and I want it to be non-degenerate, which is to say that it should span all of c to the g. The mathematician's notation to write this is this, which is to say that the R linear span of all these vectors is all of c to the g. I don't want to be contained in any real vector subspace. So the 2g generators that I have of lambda must be R linearly independent, okay? This is a complex manifold. This is a compact complex manifold. Okay. Up to biholomorphisms, which I can just obtain by changing coordinates here. Choose first G generators of lambda to be the coordinate vectors. So this means my lambda is going to be equal to just z to the g plus the remaining vectors, and the remaining vectors will be given just by a g by g complex matrix, right? So I choose this is a quotient. There are no inherent coordinates on c to the g given here. I can choose coordinates by an action of a linear transformation. This will be a biholomorphic map of c to the g to itself, of course. Will also be a biholomorphic map of the corresponding complex tori. So I just choose coordinates in such a way that the first g generator of the 2g generators of the lattice are the coordinate vectors. So they generate the lattice, not the lattice, the subgroup z to the g inside c to the g. The remaining g generators, they form a g by g complex matrix. I just write them out. And then I multiply them by z to the g. There is a disclaimer to make. It does matter whether I multiply on the left or the right. The literature is full of mistakes. I have certainly written them myself, and I will continue this wonderful tradition. Okay? So when I write tau z to the g, I probably mean z to the g times tau, and I will be very sloppy about this in the lectures. If you want to do actual computations, you better do it correctly. I will pretend that this doesn't matter, okay? Conceptually, it doesn't matter. You should do it consistently. You should make it. You can do either choice, but then in various other things I'll write whether I take quotient on the left or right, or all this stuff will matter. I will ignore this because I won't be able to track this, and that's not the point, okay? Just be aware. So that's a complex torus. Why did I not call it an abelian variety? Because it's usually not algebraic. Warning, most G greater than 1 dimensional complex tori are not algebraic varieties, do not admit an embedding into CPM. Okay? And we don't like them. They're not algebraic varieties. Not algebraic. Not projective varieties. Okay? That's a warning. And there is a theorem. This is called Riemann's theorem. And I'll write it the way I write it. The amazing thing is that this was proven by Riemann, even though he didn't have half of the language I'm using. So it says that the torus tau, maybe I should put a, okay, let's put a tau here. Can be embedded into CPN if and only if tau, which remember is a G by G complex matrix, is symmetric and the imaginary part of tau is positive definite. Okay? I will certainly not prove this. But I will say how one could write a 5-line proof of this. Not 5, but slightly longer than 5. A short proof of this from a different language, okay? So, definition. A polarized complex abelian variety is A, which is isomorphic to a complex torus which is equivalent to, say, such that points A from a group is compact, I claim that if you have any algebraic variety whose points form a group and it's compact, it's a complex torus. Together with, I'll write here the first Chern class, but I encourage you to ignore these words for the time being, of an ample, and I'll explain the word ample, line bundle. Line bundle L on A. Okay. So an abelian variety is a complex torus together with an ample line bundle L. Okay, I'll tell you in a second what an ample line bundle is. The existence of this ample line bundle is equivalent to being embeddable in a complex projective space. Okay? So definition: a line bundle L on a complex variety mathematical algebraic X is called ample if there exists an N sufficiently large such that the sections of an N times the power of N define a map that takes X and embeds it to a projective space of some dimension. So this is to say that I have, so a line bundle L means some transformation rule in our automorphic thing. I allow higher and higher powers of that. Typically, in our situations, I will have more and more sections. There are more and more theta functions that transform that way. And I want that to be enough of them so they can distinguish all points of X. So this is to say that I get a map like that. Okay? This is equivalent to saying that the first Chern class of L is positive if you know what the first Chern class is, what positivity in differential geometry means. Okay? If this is the case, let's call this map F, then of course L to the N is the pullback of the bundle O of 1 by definition on Pn, which is an equivalent definition to all of this. Okay? You don't need to read this line. This line is optional. Okay? You don't need to read any of this. Okay? Because I'll tell you what this is explicitly, but it's important that I can use this language. So explicitly, I can define, let's go back here. Let's go there. So explicitly, I'll just generalize all of this. Okay, so this blackboard will be the G-dimensional generalization. Tau will lie in the so-called Siegel upper half space. Siegel upper half space, which is the set of tau, which are G by G complex matrices that are symmetric and such that the imaginary part is positive definite. Okay. Z will be a point on C to the G. And the abelian variety A sub tau will be C to the G quotient by Z to the G plus tau Z to the G. This is what I was writing everywhere there, right? Okay. Theta of tau Z is this formula. So let me first write that formula on the nose. Okay, that was the formula I just wrote before. The only change I need to write is this. That's the formula. There is no change, right? It's the same thing, except now my n is a vector. Well, to be pedantic, maybe I should put a transpose here. Okay, so this is a vector, this is a covector, or the other way around. Again, I'm being sloppy whether I multiply left to right. But this is n transpose tau n, and this is n transpose multiplied with z, which is a number. This number, this number. Okay. The imaginary part of tau is positive definite, which guarantees convergence of this thing. Okay. And this is a section of a bundle on HC called theta tau. This is definition of a so-called principal polarization. So this is a function which has automorphic property. Its automorphic properties define a line bundle. I call that bundle Z. Okay? There is a claim that this bundle has only one section. Okay? So let me continue. For any epsilon delta in Z mod n to the G, theta epsilon delta tau Z is some exponential which you continue not to care about. Theta tau Z plus tau epsilon plus delta for n. No change. It's just the same formula. I haven't changed. This formula is just exactly the same as this one, right? Except here again, this is a vector. This is a vector multiplied by a matrix, which gives me a vector. Okay? there are now n, well, there were n squared of these guys, now there are n to the 2g of these. Okay? Because how many choices I have to choose g enters from 0 to n for each of this. Okay? I have this, theta epsilon tau z is equal to theta epsilon 0 and tau z. No change. There are n to the g of this. Okay. You notice that the only stuff on this blackboard which is new, I mean, I wrote it so that you could take notes. And if I wanted to save time, I would just add G in whatever 4 places on this blackboard. That's all I'm doing. Okay? They are bases of okay. Yeah, sorry, this should have gone up. Okay, let's go up. I can jump, but if I slip and fall, this would not be the end of the lecture, quite envisioned. Okay. Let's look at this blackboard. Here I'll just do what I should not do pedagogically, but I'll just write G here. Dimension is G. This formula here it's a G and stays the same, except this is a scalar product, right? This is now a vector of G zeros and ones. This is a vector of G zeros and ones. I can take the scalar product, which is 0 and 1, or 1. These are elements in Z mod 2. I can add them mod 2, no problem. But it's exactly the same formula. Really, nothing whatsoever has changed. What I really have to tell you is an analog of this, right? So this defines the polarization, right? So I said that actually what I really said in algebraic language is that for any tau in the Ziegel upper half space, the complex torus, which I denote A tau, this quotient, automatically, naturally, has a structure of principally polarized complex abelian variety. So it's a polarized abelian variety. Polarization is given by a divisor theta tau of the theta function. And the word principal means that the dimension of the space of sections of the bundle theta tau is 1, which is part of this formula for n equal to 1. Questions while I keep erasing? You know, if you want to have a long break for lunch, the more questions you ask while I'm erasing, the more time for lunch you have. E tau is A tau. Yeah, so E tau should have been A tau from the beginning because it's an abelian variety of dimension 1. Writing E tau for a high dimensional abelian variety, I have problems with. I mean, it's not an elliptic curve. It's not a product of elliptic curves either. It's an abelian variety. So A tau is E tau. Maybe I should have made that change. Makes no difference. Okay, theorem. This is due to Lefschetz. And I won't be able to give you a proof. So for n equal to 2, the statement is that if I take the set of all these guys for fixed tau and all epsilon in z mod 2 to the g, right? This in genus 1 gave me a 2-to-1 map of an elliptic curve to P1. All of these guys are always even functions of z. You can check from my formula, they're always even in z. So what they're really defined on, they're defined on the quotient of a tau by plus minus 1. They cannot distinguish the point z and minus z. The value of this at z is equal to the value of this at minus z. And this gives me an embedding in the projective space of dimension 2 to the g minus 1. There are 2 to the g of these guys. I consider them up to scaling because they are sections of a bundle. So under the automorphism, they scale all the same way, so I can only map to a projective space. Okay? And for n greater than 2, these guys, for epsilon in z mod n to the g, give an embedding of the abelian variety itself. Okay? So for higher levels, it is not true that all sections are even, and in fact, they do everything. This is a generalization of what was written on the blackboard here and what I mumbled for elliptic curves for genus 1. So for an elliptic curve for genus 1 Riemann surface, the two thetas here gave a degree 2 map to P1, right? Which I'm now interpreting as an embedding, actually, an isomorphism in this case, of an elliptic curve quotient by plus minus 1 with P1. And then I told you that for higher n, I told you about n equals 3, that I get an embedding of an elliptic curve at genus 1 Riemann surface and P, well, to the 3 minus 1, which is P2. Okay? I won't be able to prove this theorem for you. This requires some work. Okay? There are ways to cheat your way out if you know a lot. If you say the words moduli, then you can check that this is injective somewhere. And if it's injective at one point, this will be generically injective. Whether that's going to be then injective at every point is a pain. I won't go there. Okay? So that's a fact. Meaning, fact means this is a true theorem. I know a proof. I'm not telling you the proof. Okay? Okay. So far, so good. Let's look at this. This map is called the Kummer map. Kummer embedding. I'll write cum for it. Okay? Yes? This is only the, yes, so it's only called this, this is called the theta embedding, if you call it anything. This is called the Kummer embedding because the quotient of an abelian variety by plus minus 1 is the Kummer variety, which is embedded by the Kummer embedding in the projective space. Okay? My focus will be here. From now on, n will be 2. I may mumble something about higher n, but I won't. My focus will be just here for the reason that, n 2 to the g is already a large number, and 3 to the g is a much larger number, okay? You can say more things. Things become more regular in some way for higher n, but the formulas become more complicated. Most formulas you encounter in real life are for n equal to 2. Most, not all, okay? And we have a limited amount of time, so n is going to be 2 from now on. So this means I have the Kummer map, which takes my quotient by plus minus 1 and embeds in here, right? For g equal to 1, Kummer map is an isomorphism. That's what I told you before, right? This map just exhibits an elliptic curve quotient by plus minus 1 as P1. For g equal to 2, the Kummer image of an abelian surface inside P3 is the famous Kummer quartic. Okay? I won't tell you what it is, but it's a surface. It's codimension 1, right? It has dimension 2 in a 3-dimensional space. It's given by one equation. The equation is of degree 4 in homogeneous coordinates in P3. It's completely known. And if you think this is boring, there is a book called Kummer's quartic surface. Okay? It's a book, and there are many papers. And there are still open problems you can ask. Okay. Hundreds, well understood, I think is what I want to say here. For G equals 3, the Kummer image is 3-dimensional, of course, inside a 7-dimensional space. You should feel bad. Okay? This is complicated. This is not a complete intersection. It's not just given by 4 equations. And there are hundreds of papers. I have only contributed maybe 1 or 2. Okay? So you can try to understand what this looks like, but it's a complicated question. So what is this question really about? So I take this map and I try to see what equations are satisfied by the images. So what is this question really about? The question is, what are the polynomial equations satisfied by theta functions? Maybe in this guys you would care about such a question. That's what this is. This is just an algebraic statement of that question. Huh? Oh yeah, the degree is known for any genus. It's an easy computation. You can guess. The formula, this is 4, this is 1 or 2, depending on how you look at it. It will be fine. You can compute the degree, you can compute the homology class, you can compute many things. These things are singular, so be careful, but there is interesting stuff. Huh? Yeah. No problem. I mean, many things are known, it just, so say it again? Oh, tau is fixed, yes. I am very glad that you're asking. Thank you. This is exactly the next section of this lecture course. So all of this was for tau in the UK, tau. Okay. For that letter being fixed. No. Okay, I'll say tau for the rest of today in honor of Francis. Yeah, I can say both. So all of this was for tau fixed, right? And this is on one abelian variety. You fix your tau, and you consider the abelian variety A sub tau. And then you see what happens. And the foundational papers in this direction that study the equations of one abelian variety really embedded like this or in higher ends are due to Mumford, and they're in 1960s. Okay? And these are really foundational papers. And they tell you a lot about the ideal of relations among theta functions, the ideal of one abelian variety as embedded in a projective space. Okay? And I think I'll check that this is really everything I wanted to say about this story. Okay? Yes? Yes. Yes, they are not going to be 3-term identities. You can prove that you will never have 3-term identities. By looking at this formula, right, you will again write many identities. They will have more than 3 terms. You can ask what is the minimal number of terms they have that's known. I would argue that's a boring question again, because this is just some kind of Veronese embedding, and you are just asking what is the minimal number of terms and an equation for the Veronese image of something. Known, but unless you have a good reason to investigate this. These are basis of sections, these are not. So somehow the questions should be phrased in terms of this to have more geometric significance. Otherwise, it's a combinatorial question. Okay? Any other questions? Okay. Change of gear. Thank you, Francis. We'll vary Thor for the rest of today. Mm-hmm. Excellent question. This is very hard in general, because the symmetries of Thor that you get they are automorphisms or endomorphisms. And we are talking about abelian varieties with automorphism, which is small, or with endomorphism, which is a large set. And you can ask whether these identities will know something. This is a question about syzygies between sections of powers of theta. So there is a machine that somehow tells you take sections of 3 theta, multiply them, you get sections of 6 theta. Are any special properties of an abelian variety detected by that? The answer is some are, most aren't. It's complicated. If the abelian variety is a product of lower dimensional things, you can detect this, but it gets complicated. But this is, again, a great question to ask now because we're now going to vary Tor. Okay? So this comes under the guise of moduli spaces, which means we vary Tor over the Ziegel upper half space. And also in genus 1, but here I'll try to do the theory for genus, arbitrary genus from the start. Okay? This is something we have not done. I have tried to keep Tor in all my formulas, but it was always fixed in our discussion so far. That's probably a bad thing to do. Okay. So the basic question is, how does theta of Tor z depend on Tor? Okay? And for a while, for now, I'll just set z to be 0. Look at so-called theta constants. And I would like to do them, not just the theta itself, but all of them at once. Okay? Looking at the clock, I think, there is a beautiful theory how you go from this discussion to non-zero z, and this is degeneration in the moduli of abelian varieties, and you get from Ziegel modular forms to Ziegel Jacobi forms. I hope somebody will ask me during the Q&A later today how this works, okay? I'm happy to tell you privately, but it looks like I won't get there otherwise. So these are called theta constants. That's a classical name. It's a horrible name. It's not a constant. It depends on Tor, right? But the constant means it does not depend on z. And I'm about 150 years late to change the name, so we'll call them theta constants. So what does it mean how it depends on Tor? That's a silly question. It's a function of Tor. It's a holomorphic function, as everything I've written. It's a holomorphic function of Tor. Aren't we just happy? No, we're not happy. The reason we are not happy is we can ask the following question. When is an elliptic curve E Tor isomorphic to some other elliptic curve E Tor prime? Raise your hand if you know the answer to this question. I'm just trying to gauge. Okay. So if I have isomorphic, just means I have a biholomorphic map, right? E Tor is a quotient of C by this. This is a quotient of C by Z. This. If I have a map from E Tor to E Tor prime, which is an isomorphism, you can argue, this is easy, that this comes from an isomorphism of C to itself, so it leads to the universal covers. And this is supposed to be an isomorphism. What are holomorphic maps from C to itself? They're linear. Well, they're affine linear, but I can as well require the 0 to be mapped to 0, right? So this is linear. So this map means any isomorphism of one elliptic curve to another must be covered by a linear map of C to itself. A linear map of C to itself is just a multiplication by a number, by a complex number, right? But when does such a map descend? When does such a map induce a map of elliptic curves? I need the lattice to be mapped to a lattice. So answer, that's an exercise. And I highly encourage you to do this exercise if you've never done it before. This is essential to understand how this thing works. E sub Tor is isomorphic to E sub Tor prime if and only if there exists an element gamma, which I'll write as A, B, C, D, in SL2Z, such that tau prime is A tau plus B, E tau plus D inverse. Okay? So this just means I have a lattice, Z plus Z tau, and I want to map it isomorphically to the other lattice. So the vectors 1 and 0 will have to map to two lattice vectors, which are A tau prime plus B and C tau prime plus D. That's how I get the ABCD. Okay, that's an exercise. Okay. So what this means is that SL2Z acts on the upper half plane, right? By this. You can check that indeed the imaginary part will stay positive. That's an easy check. And then H quotient by SL2Z, yes, I'm writing this on the left because customary, is this picture. Okay, this is 1, this is I, this is third root of 1, this is sixth root of 1, this is the third root of 1. They leave over 1/2 and minus 1/2. Okay? What does this mean? This means that if I give you any point on the upper half plane, by acting on it by SL2Z, I can make it end up here. That's part of your exercise. You really should do it. Okay? It's not hard, it's just an explicit computation with SL2Z. Very essential. If you know how to do this, there is an exercise with a star, which is to see all the points with automorphisms and endomorphisms in this picture, okay? Which you can do. I am well aware. You can probably guess why. Okay, that's the situation in genus 1, okay? And then what you can ask is, how does this theta function, or theta functions with characteristics, I want the full strength, change? So the question is, how does this guy differ from this guy, prime, if tau prime is obtained as such an action? This is the definition of an action of gamma on tau. Okay? And that's the question I'd like to answer, but since we don't have so much time and the formula in higher genus is really not much harder than in genus 1, I'll just write the general formula from the beginning and state, give the definitions in general. Fine? Good? I think I can erase all of this. Okay. Next question. So I want to just do the same Blackboard, but in higher genus. Question. For two elements in the Ziegel upper half space, so two G by G symmetric matrices with positive definite imaginary part. When is the abelian variety A tau isomorphic? Notice I left space. When abelian variety A tau prime. Okay, bad question. You'll get something unpleasant if you follow through with this. You really should say with the polarization, with the polarizing divisor. Okay. So what I mean by this, I want an isomorphism that will send this to that. Okay. This is a divisor, but theta tau prime, I can also view theta tau, I can view as the locus of z in A sub tau, such that theta of tau z is 0. So I can view this as a line bundle, I can view it as a zero locus, I can view this as an automorphic factor, and I'll view it in all of the above ways. Here, you should really view this as a first Chern class, so this means up to translation. Okay? You have to do this. Why do you not see this in genus 1? Because in genus 1, your elliptic curve, your genus 1 Riemann surface has it's an elliptic curve. We're all used to adding points on that. But when we're adding points on the elliptic curve, we've chosen the point 0. The point 0 is a point. We're very happy with that point. The point 0 is also the theta divisor up to translation. In higher dimension, if I chose a point, that's not the same as to choose a divisor, which is a codimension 1 locus. So there is a big difference. So choosing 0 in higher dimension is not the right thing to do. We'll suffer through that in 2 days on curves. This is an important technicality, but that's what you need to do. Okay, and the answer is, that's a serious exercise. If and only if there exists gamma, which I'll write as A, B, C, D in the symplectic group with integral coefficients. Okay? I won't write down the defining equations of symplectic group. A, B, C, D, these are 4 G by G blocks. And the symplectic pairing is 0, 1, minus 1, 0. Where these are also G by G blocks, okay? And this is supposed to preserve that pairing. So this transpose times that is equal to this again. Okay, that's the symplectic group. Such that tau prime is gamma composed with tau, where this action, gamma tau, is defined to be let me make some effort to write it in the right way. Okay. I think the correct order would be this. I may have made mistakes here. Maybe this factor goes on the right. It may be A tau or tau A. The same here. I probably have made it inconsistently somewhere. That's a feature. It's the same formula. The same formula as before, right? Except this is now a matrix, right? This is C is a G by G matrix, G by G integral matrix, G by G integral. This guy has positive definite imaginary part. So this whole thing is invertible because the imaginary part just comes from here, and that's positive definite and particularly invertible. You get this. You need to check that the imaginary part of this whole thing is still positive definite. Good luck. I mean, true, but not immediately obvious. You need to check that this is still symmetric. Well, if I didn't write things on the left-right correctly, it won't be, so good check. But this is correct. That's a statement. Let me say in 1 minute how you will prove this without computation, which is not what I'm suggesting. A polarization is a first Chern class of an ample line bundle. It's an element in the second homology group with integral coefficients because it's a first Chern class of an ample line bundle. It's also a first Chern class of an ample line bundle, so it's an H11 in de Rham cohomology. That's equivalent to given an integral antisymmetric non-degenerate pairing on H1 of an abelian variety. The H1 of an abelian variety is C to the G. The non-degenerate pairing is that. So you have to preserve the polarization, so you have to act by that. Okay. Almost true. I mean, I have to expand this, each of these words to a sentence. This would be a proof of this, which I'm not suggesting we pursue now. I certainly won't because I don't have time. Yes. I mumbled somewhere under my breath up to translation. Whether theta is really the Chern class of theta, here it doesn't matter. But basically, yes. which is the same as an isomorphism of these things, which preserves the intersection pairing. So if I have an isomorphism of one complex torus to another, similarly to that, it will lift to a linear map of C to the G to C to the G. That's how I see a linear map. But why would the complexity group appear? Why does the SL2Z appear there? It's because I have to preserve something. So what I was mumbling was to say that the linear map of C to the G to C to the G that I see will actually be given by a symplectic 2G by 2G integral matrix. I'm not proving this. I will prove very few things in this class. I will prove phase trisecant identity next time based on some things I won't prove. Yes.
Okay.
There is a fundamental domain. It's called the Siegel fundamental domain. It is written in papers by Siegel. Papers by Siegel are notoriously hard to read. This is known. You can do it. In genus 2, it's very explicit. People have used it. You can do it in higher genus. It's something in a G times G plus 1 over 2-dimensional space. Not so easy to draw. You can do this. You know generators for sp2gz. You can do some kind of Voronoi Delaunay decomposition. You will find a fundamental domain. This can be worked. I am not sure how much mileage you get from that. Typically not as much as you would hope because it's complicated. It's the sort of combinatorics and the structure of this fundamental domain is not so easy. There are, of course, many choices. I mean, I've drawn this fundamental domain. There are different ones. Siegel's choice is one particular fundamental domain. There is an a priori way to define a fundamental domain. You just take a point, a tau. You take its entire orbit on the sp2gz. There is a natural metric on the Siegel upper half space. You just do the perpendicular bisectors, whatever they're called. Things that they connect a point to its orbit point. There was a segment, the geodesic and the metric. You just draw a plane, a hyperplane perpendicular to the midpoint. This will give you a fundamental domain. Whether you can write this down in a useful way, yes. I mean, you can write this down. Whether it will be in a useful way, that depends. Okay? Did I answer your question? Or? Okay. Definition. A holomorphic Siegel modular form. So a holomorphic scalar valued of weight A for a usually finite index is what is useful for a subgroup gamma in sp2gz. If G is 1, sp2z is sl2z, so I recover the usual case, is a function f from the Siegel upper half space to C such that for any gamma in here, gamma I keep writing as A, B, C, D, f of gamma tau, is equal to the determinant of C tau plus D to the K f of tau. Okay? Hopefully this is K and not minus K is the way I wrote it. In genus 1, there is no determinant. It's the usual notion of the Siegel modular forms you all know and love. No difference. Okay? Algebraically. So what does this mean? So let A, G, gamma be the quotient of Hg by gamma, be the so-called moduli space stack of principally polarized abelian varieties with level G structure. That's just a name for these things. Because that's the moduli. I'll say more about this in a second. Then there exists a line bundle L here, even without a G, of modular forms of weight 1 and this thing here is equivalent to saying that your F is just a section of this bundle over K. The same as for the dependence on Z, right? The dependence of the theta function on Z, this was an automorphic factor. It says that if I go around the fundamental domain for the action of the lattice on C, it multiplies a certain way. The same here, I go around the fundamental domain for the action of sp2gz on the Ziegler upper half space. And the modular forms transform that way. And this way is always a k's power of some function, right? So if k is 1, this is some transformation law. This defines a line bundle on this quotient, okay? Just by this transformation law. And then all this is to say we take sections of a line bundle to the power k. Okay, is the definition good? Somehow that's the main definition, if you wish, for today. Learn the lesson not to push this where I cannot reach it. I'm aware that I have to stop in 5 minutes, so maybe 7 minutes, but we'll be there.
Is there a natural splitting in terms of Eisenstein series?
No.
Cusp forms?
Sorry, I mean, there is a well-defined notion of cusp forms, and that's fine. These are things that vanish at the boundary. If I were allowed to say the word boundary, which you could ask me later today, because that's exactly what the whole story about Ziegler-Jacobi forms is. Saying the word Eisenstein series, you have to be careful, because I'd like to know what you mean. So there are the modular forms which are not cusp forms. That's a perfectly well-defined space. When you say Eisenstein series, you probably have in mind some construction of these things. That's an interesting question. More questions? Okay. Definition. Gamma n is the set of gamma in sp2gz such that gamma is congruent to 1001 mod n. Okay, this is just matrices in the complexity group such that their entries, I mean, these are blocks, right? These are G by G blocks. This is the same as gamma n in genus 1. If you just squint and this looks like SL2Z to you, that's the definition of genus 1. This is a principal level n subgroup. If you try to ask what is its index, what is the number of elements and the quotient of this by that, that's a normal subgroup. That's the number of elements in sp2g z mod n. It's a large number. This is the index of the subgroup is huge. Okay, this thing here is the most common one. For me, I have another one, which is, this is gamma in gamma n, such that the diagonal of A transpose B is congruent to the diagonal of C transpose D is congruent to 0. The diagonal means it's a vector of G things, mod 2n. 2n, right? So mod n is automatic. A is congruent to 1, B is congruent to 0 mod n. So this is to say B is all divisible by n. So this guy is certainly all divisible by n, but I want by 2n. Not clear that it defines a subgroup. When you look at it, you can check. This is called the theta level n subgroup. Okay. Fact. For any n, remember this was my capital N, which I usually set to be equal to, but this I want to state in general. Theta epsilon delta tau 0 is a modular form greater than 1, otherwise I don't know what I'm talking about, is a modular form of weight, my k, equal to 1/2. I have to take a square root in my transformation formula for the group gamma 2n, 4n, I think, in my notation, yes. 2. Okay. Theta, the other guy, the other thing, he is a modular form of weight 1/2 for gamma n 2n. Okay. That's a fact. So that you know the formula, in general, for n equal to 2, for any gamma in the full simplicity group, the transformation law is as follows. Where rho is an 8th root of unity, so there is some transformation law which is more general, which somehow says that if I just try to act by any element of simplicity group, and I'm just restricting myself for simplicity to n equal to 2, the characteristic will change. The characteristic epsilon delta will map to another characteristic, which I know how to compute. There is a simple formula. There are some diagonals showing up for these diagonals. And then there is an 8th root of unity, which is a mess. Yes? That's what I meant. Gamma applied to top. Okay, that's a general formula, but that's more complicated. That's what I want to state. Okay. Yeah, this n z mod n to the g, as usual. So again, the most useful case for us is n equal to 2. Now let me take 2 minutes over time to say where this is going, and we'll be done for today. So what I wrote was AG. I wrote for gamma, but if there is no choice of gamma, I just take the quotient by sp2gz. What this is the moduli space of principally polarized abelian varieties, which is to say this is the same as the set of all principally polarized abelian varieties up to isomorphisms by the exercise over there, right? 2 abelian varieties are isomorphic if and only if I can get from one to the other by an action of this, right? L is a line bundle. This is a bundle of modular forms of weight 1. For any gamma in sp2gz, the AG gamma to AG is a cover. Okay. Theorem. If I take AG with level 4, 8, so gamma 4, 8, is embedded in a projective space of dimension, well, actually 1/2 of this, but never mind, by taking a point tau and sending it to the set of all theta constants. That's a hard theorem. This is a theorem of Igusa and Mumford in different viewpoints. It's certainly not easy. In the algebraic geometry language, what it says is that the bundle L to the 1/2 here is very ample, not just ample, not just positive, but defines an embedding. So this is to say that we can recover an abelian variety from the set of these theta constants. This is Mumford, Igusa, Mumford, 80s, 70s, depending on how you look at it. Theorem star AG gamma 2, 4 has an embedding in P to the 2G minus 1 by sending the tau in here to the set of the other guys. That's the theorem of Salvati-Mani, which you can read. There is only one problem with that theorem: the proof has a gap, which still has not been fixed. So you know that this map, what is known is that this map is finite, generically injective. Okay? So there are some technical issues. What does this all tell you? This tells you that if you want to have some approach to understanding moduli of abelian varieties, if you want to vary the tau and see what you get, the moduli space you get is embeddable in projective space. And you can ask, what are the equations for the images? Of this maps, well, I'll call this theta 2, and I'll call this theta 4. And this is known for G up to 3 and open for G up at least 4, which is to say we don't know the ideal of relations among Ziegler modular forms fully in genus 4 and higher. Okay, that's what I wanted to do over time today. So this was moduli of abelian varieties. One thing I did not do is I didn't tell you how to go to the boundary and expand Ziegler modular forms into Fourier Jacobi expansions to get Ziegler Jacobi forms. That is not going to be covered next time. So next time we'll talk about theta functions on higher genus Riemann surfaces. This will be related to this, but will be different, and we'll prove phase tracing. Thank you.